Hello class. So today what we'd like to talk about is even functions and odd functions. Uh, this is something that we already have learned in pre-calculus, but we'll try to briefly review a little bit one more time. Now, uh, as we begin, I would like to ask you guys to do one thing, which is do now right over here. I will just try to sketch the functions below, right here, these three functions. Now, if you want to, you can use your graphing calculator. So now, let me give you a little bit of time for you guys to work on, and we'll continue right after this one. All right, so I guess you could have paused the video and then work on it, or we can just continue at this point. Now, when you look at y equals x squared, this is rather common. We know that the graph would have looked something like this, going up this way in both ways. Now, and then y equals x to the fourth minus 3x squared. Actually, you know what? I may not be able to know right away, but if you had to graph it, we know that this value would have gone through a couple of x values right here. So what I have done was I made up the sketch of each function. So for example, this is the function of y equals x squared, as you can see right here. Now, y equals x to the fourth minus 3x squared is actually right over here. It looks like a W shape, isn't it? Now, because this is fourth power, we will realize that you will have 320 points and so forth and so on. How about here? Y equals x to the sixth power plus 5x squared. If you have to sketch this one, you can see that it's increasing very rapidly, going all the way up to 150. In fact, this exponent is so huge compared to this one, so dominating function would have been the dominating part of the function would have been x to the sixth power. So these are the three sketches which you could have done using your graphing calculator. Now, then my next question is this: seeing all these things between these three functions, what is common amongst these three things? All right. One goes this way, another one goes this way, and third one goes this way. Did you think about that? Yes. In fact, yes, that's right. One thing that's common amongst these three functions is that these three functions are symmetrical about the y-axis. In fact, about this y-axis, the function to the left is equal to the function to the right if you had to fold it over. Same thing here. This function is also symmetrical about the y-axis. As you can see, this portion is mirror image of the other one. So as this one right over here. In fact, this is no coincidence that this one happened. In case of polynomial functions, especially when you have certain characteristic of the polynomial functions, you will see something like this. Functions will be symmetrical about the y-axis. Now, then next question is this: when you look into these three algebraic expressions, what is common amongst these three functions? Okay, think about that, guys. Did you get to see what is common amongst these three functions? Yes, that's right. The exponent is, in fact, quite interesting. Did you realize that exponents are all even numbers? Yes, I understand we have some coefficients that are odd, or one that's being hidden for that matter, but in fact, when you look at the exponents, they're all even, which makes sense because whether you plug in positive numbers or negative numbers, you will always get positive numbers, or same values for that matter. So in fact, mathematicians a long time ago, when they were thinking about this one, hey, wait a minute, when the exponents are even for a polynomial simple functions, you will realize that graphs that are symmetrical about the y-axis. So here it goes, guys. What's actually happening? The even function here even functions are symmetrical about the y-axis. Now, if you had to write this symmetrical about the y-axis in algebraic form, then you're doing something like this. Let the function be f of x, but when you plug in negative x, the result will be same thing as when you plug in without, you know, negation sign, negation of that value, which is you can say positive value too. In fact, positive value. When you plug in positive value versus negative value, when x is positive, you would have gotten the same y value. That's basically what it means by being symmetrical about the y-axis. Now, obviously, you guys would have figured it out by now where the name even would have came from. Yes, it is from the exponents of the polynomial functions. All right, now, then given that, I have another set of questions that I want us to look at together. How about y equals x cubed? Next one is y equals x cubed over 6 minus x. Now, this one is rather popular. So in fact, if you had to sketch this function, it would have been something like this. About 0, you're going to go up very high. It looks like a parabola looking thing, but in fact, it's not quite. When you go down, it's going on the left side, it's going to go down a little bit. I noticed that it went up about the x-axis a little bit, but that's just graphing error, but rather it's just going down. In fact, this will be the look of x cubed. Now, this one is somewhat more complicated. So what I have done was this. I recorded the image of these two functions. Now, in your case, you can try to do that yourself. All right. So now, I'm going to assume that you already looked at it a little bit using your calculator. If you didn't, you can pause this video a little bit and then try to work on those. All right, here it goes. As we talked about it earlier, yes, the y equals x cubed looks somewhat like this. It looks in this way. Obviously, this is not symmetrical about the y-axis, but let's talk about this one very soon. Next function. It looks somewhat similar to previous one, but as you can see, it's going up and down a little bit more. And once again, this is not symmetrical about the y-axis. Now, then my question is this. What do you realize about these two functions? If they're not symmetrical about the y-axis, what are these two functions symmetrical about? Have you ever noticed that? Yes, that's right. These two functions are symmetrical about the origin. Right over here. If you had a very small mirror and showing this image through that mirror, then you would have seen something that looks like this about that particular point. Now, same thing over here. Given that, then okay. If you had to plug in a positive value x here, and same distance has been gone to the left side around here, if this one is a negative x, what do you realize? Here, the value of y value was positive, while this one would have been y value is negative, isn't it? So in fact, these phenomena was observed, especially when you have a polynomial functions with exponents that are odd. Yes. And in this case, what do you think we're going to call these functions as? That's correct. We would have called these as odd functions. Yes, in case of odd functions, they are symmetrical. About the origin. Now, then in this case, symmetrical about the origin. So therefore, let's try to look into this one a little bit together. Then how would you write down the algebraic expression of the odd functions? So similarly, when we plug in f of negative x, given that x was the positive number, in this case, the way when you plug in negative x into the same function, the way they behave is kind of the opposite. If one was positive, the other one would have been negative. If one was negative, the other one would have been positive. In other words, when you plug in negative x, that will carry the same value as f of x, except that it is negation of that. So in fact, this is the algebraic definition of an odd function. Now, so these, when you look into these two, these are the basic definitions of even and odd functions. Now, what we like to do is this. Let's try to explore this one a little bit more and continue and see what happens. Some other popular functions which we have to realize about even and odd would have been following. So let me just get you a couple more questions here. Number 6. How about y equals sine of x? What do you think about this? So let me give you a little bit of time. Number 6 would be a y plus sine of x. Number 7 would have been y equals cosine of x. See how or which one of them would have been even function or which one would have been the odd function. Okay. Alrighty, then let us continue here. If I have to just, put up one small arbitrary graph here. You'll realize that the sine of x would have looked something like this. And in fact, the other side would have looked something like this too. And then, how about cosine of x? Cosine of x would have looked something like this. And the other side would have been something very similar. Now, as you can see, what happened in case of sine of x? You will realize that this, in fact, is symmetrical about the origin right here, isn't it? And in fact, this makes sense because we know that, as we have learned in trigonometry class, what is sine of negative x? In fact, you will realize that this is equal to negative sine of x. You see? How about here? In case of y equals cosine of x, yes, in this case, this is symmetrical about the y-axis, isn't it? Yes, and also, algebraically, cosine of negative x, what is this equal to? Same as cosine of x. Yes, so therefore, we realize that this is an even function. And this becomes odd function. All right, let us examine a few more questions, and then let us see what happens. Now, next one. What if I were to give you something like this? Number 8. I believe it is number 8. Yes. Y equals x to the 4th power plus x squared plus 1. How about this? Now, number 9 would have been this. Y equals x to the 5th plus x to the 3rd plus 1. I want you to examine these two functions. And I want you to tell me if which one of these are even functions or odd functions for that matter. And we'll continue. You can pause it a little bit and then work on this one. All right, so let us continue here. What do you think about the first one, number 8? Y equals x to the 4th plus x squared plus 1. Yes, that's right. When you look into the exponents, as you can easily see, that this gotta be an even function. Now, and you can algebraically see that when you plug in negative x. So for example, y equals negative x to the fourth power plus negative x squared plus 1. Yes, because of square and the fourth power, these negative signs would have been cancelled out and become same thing as that. And even if you have to graph it, as you can see, you see the symmetry about the y-axis right over here. All right, how about number 9? Number 9, yeah, it looks like an odd function. Looks like, because you see 5 here and then 3 here. But let us try to sketch it and see actually what happens. If you had to sketch this function, you would have gotten something like this. It looks somewhat similar to previous questions here, but as you can see, one major difference between these two pictures to this one is this symmetrical about the origin? That becomes a question. Origin is right here. Is this symmetrical about the origin? The answer is no. In fact, it is symmetrical about this particular point, 0, 1. In this case, is this an even function or odd function? The answer is neither. It's not even nor odd. Now then, some of you guys might be asking, hey, Suk, how does this make sense? 5 and 3. Because we see odd exponents. In fact, if you look into 1 carefully, you can say that 1 in fact is multiplied by x to the 0 power. In other words, when you look at the exponents here, 5 and 3 and 0, you see these are odd numbers, but this one is an even number, mixed up together. Sorry. Therefore, this one is not an even nor odd function. All right, so as you guys can see, sometimes even functions can be mixed with odd functions. So now, next part of the lesson, what we like to do is this. We like to look at these even functions and odd functions, and in conjunction with operation on functions, such as this one. So number 10, here let us assume that let f of negative x is equal to f of x. And g of negative x, let us assume that this is equal to negative g of x. Now first, what I'd like to ask you to do is this A. Can you tell me determine if h of x, which I'm going to explain what those are, is even function or an odd function. Okay? Now let's look at the first one, h of x. What if I were to say h of x is in fact equal to f of g of x? Let me compose these two things together in this way. In order for you to tell me, hey, is this an even function or odd function? What are we going to do? Because we have no idea what f looks like or what g looks like. Yeah, I guess we can try to use an example, but why don't you think about that a little bit? Okay? All right, so I'm sure you had enough time to think about it. Yes, you could have, excuse me, you could have paused it if you wanted to. But in order for us to test if h of x is even or odd, what we like to do is this. All we have to do is, in place of x, we just have to plug in negative x. Now, if this one becomes h of x, then we know that this is even, just like what we talked about it. But if this one becomes h of negative x, then we know that this one becomes odd function. So we'll see how this one turns out to be. When you plug in negative x, then we will end up getting f of g of negative x. All right, now how are we gonna evaluate this one? But when you look into upper portion right over here, you'll see that when g of negative x is in fact equal to g of negative x is in fact equal to negative g of x. You see the negative sign? So in this place, we can locate this one, replace with this expression, which is right over here. So in fact, what we can do now is that we can rewrite this one as f of, since this can be rewritten as this one, negative g of x. Now, how does function f behave? When you look into function f, when you have negative of this is substituted in, that's equal to f of same thing but without the negative sign. F of negative this is equal to f of this. Yes, it's kind of funny I use the word this, but when you look into this one, f of negative this would have been equal to f of simply this without the negation sign. In other words, f of g of x. Oh, wait a minute. This looks somewhat familiar. Because when you look into f of g of x, that's in fact equal to h of x, doesn't it? Equal to h of x. Haha, wait a minute. When you look into this one, since h of negative x is ultimately equal to h of x, that means this one must be an even function. All right, great. Let us look into the next question. What if I were to say, in the same context, b, what if I were to say h of x is equal to g of g of x? What do you think we'll be getting? Okay, let's try to look into this one and see what happens. In order for us to evaluate what h of x is, whether it be an even or odd, what we like to do is this, just like before. Let's plug in h of negative x. Now, then, same as h of negative x, we're going to have on the right side g of negative x. But how does the function g behave? When you, since this is an odd function, when you have negative sign inside, it comes to the outside, as you can see. This will be equal to, we're just going to play with this inner g of negative x. That becomes g of negative g of x. Notice that the negative sign in the inside actually came out of g, and it's now in the outside. All right, when you continue further, as you mentioned, the function g behaves when you have the negative sign inside of that. Since this is an odd function, this will be equal to negative g of x. But wait a minute, g of x was equal to h of x. So if you have to rewrite this one, this will be equal to negative h of x. Wait a minute. H of negative x is somehow ultimately equal to negative h of x. That means this function must be odd. All right. Let us look at one more example. Or actually, two more examples. Number C. What if we have h of x is equal to, how about f of x times by g of x? We're going to multiply these two functions. Actually, not with the dot, but we're going to multiply these two functions. Right? Okay. And then what are we going to do? To test this one, once again, what we like to do is plug in negative value, or negative x in place of x. So h of negative x. What is this, in fact, equal to? Then we got to have f of negative x times g of negative x. Now, but if you remember, how does function f behave? Since this is an even function, when you plug in negative sign, this will be unaffected. simply becomes f of x. But on the other hand, how about g of x? G of x, when you have negative sign, it becomes negative g of x. Haha. Then when you multiply these two things together, we will end up having negative f of x times g of x. Wait a minute. F of x times g of x was h of x, but in this case, what do we end up getting? We end up getting negative of that, so this would be equal to negative h of x. Oh, we started with h of negative x, ends up with negative h of x. This function must be all right. The last question, number D. When you look into this one, we have h of x, let us say is equal to, what if I were to say f of x plus g of x. What is this? Is this an odd function or even function? That's right, we'll try to plug in negative sign once again. So here we have h of negative x. What is this equal to? F of negative x plus g of negative x. Now, but since the function f of negative x is equal to f of x, we call that even function, and g of negative x will be equal to negative g of x. But wait a minute, what do you realize? Is this in fact equal to or any part of h of x? No, this is not h of x nor negative h of x either. So therefore, yes, in this case, the answer would be neither. This is not an even function, nor the odd function. Something similar like this, we talked about it earlier. Right, in this case. You see how when we have odd function added onto the even function, we end up getting neither. Same idea was discussed on part B. All right, so as of now, we're going to wrap it up in this way. And have a great day, guys. I'll see you guys later.